Hi, welcome to this lecture, an introduction really to temperature and heat. We'll not cover all of chapter 10, but maybe about, the first half of it or so. And so there's a lot of terms in here I think that people are already familiar with, but we want to tighten up the definitions a little bit to be more scientific. So temperature, what does it mean when we describe the temperature of something? Really, it's a scale that we kind of invented, and what it really is telling us is it's telling something about the motion of the molecules in a substance, right? So when we say the temperature is rising or it's getting hotter, what we really mean is that the average motion of the molecules in that substance is actually getting more vigorous, right? So they're actually moving faster, and so higher temperatures mean higher motion. Now, over time, people come up with different scales here. So the de facto scale for most of the world in the scientific community is the Celsius scale. And the Celsius scale is set around water, right? Which is probably the most important sort of material on Earth here. Our bodies are mostly water and all that kind of stuff. And so that's the scale that's set. 0 degrees is the freezing point of water at STP, standard temperature and pressure. And the 100-degree mark is set at the boiling point of water at STP also. And so then you just divide that up into 100 equal increments, and then that's the scale. And so if you have a scientific formula, or you go anywhere in the world but the United States, right, that Celsius is the way to go. We still do have the older version, that temperature scale Fahrenheit. I think, we're probably the last country in the world to still use it. So there's still lots of legacy items there. That's the one where freezing is at 32 and boiling is at 212. And the reason why those numbers are there is because historically, when that scale was being developed, it was easier to find pure substances of other materials, I think is my understanding. And so they were doing the freezing and boiling points of substances other than water to set those. And so not only are the points different, right? The numbers are different. You have to scale it this way, but also the size of the degree is different, right? So the formula to go back and forth between Celsius and Fahrenheit involves scaling and scaling both ways, right? A linear scale and a dynamic scale. And there's one other temperature scale that is the truly scientific one. It's usually not a big deal because the degree sizes are the same as in Celsius, and that's the Kelvin scale. The advantage to the Kelvin scale, so if you get warmer by 10 degrees Kelvin, that also means you have gotten warmer by 1 degree by 10 degrees Celsius. That's what I mean by the size of the degrees are the same. And of course, that doesn't work for Fahrenheit, right? It's a different number. But what happened is after they invented the Celsius scale, what they realized is that the fact that the temperature is related to the motion of the molecules means that you can have a lowest temperature, because think about, instead of getting hotter, think about what it means to get colder, right? You get colder, things are moving more and more slowly. And you can imagine getting things cold enough so that they don't have any energy and the molecules themselves are no longer moving. And then you couldn't get any colder than that, right? You can't go slower than being motionless. And so that is a temperature known as absolute zero. And even though you can't actually get all the way there, you can approach it, right? And so by graphing it, you can see where it would kind of cross the y-axis, and that value turns out to be somewhere very close to negative 273 degrees Celsius. I think it's negative 495 degrees Fahrenheit or something like that. And so Lord Kelvin said, that's really the 0 point, right? We have negative degrees in Celsius. That just means it's colder than the freezing point of water, but there are plenty of days, and places and things that are far colder than the freezing point of water. And so the negative sign really doesn't mean anything in temperature. So he said, let's just set the 0 at absolute 0. That way the temperature 0 is the lowest, and then you only have positive numbers going up. So really Kelvin is the most preferred scale. Okay, so when I said that the temperature was a proxy for the motion of the molecules, really, let's be more precise, temperature is a measure of the average kinetic energy of the molecules, right? So kinetic energy is the energy that objects have in terms of motion, right? So it's a little bit more, you'll learn about it in physics, a little bit more than just the speed, but it basically, it has to do with the mass of the object and the speed. So you can think about what's the difference between a ball that's sitting there and a ball in motion. The ball in motion has kinetic energy, right? Because it has that energy of motion. Now, there are two other types of energy that I'll mention. There's potential energy. So if you take a rubber band and you stretch it out and hold it there, right? There's no energy of motion there, so you could not claim that it had kinetic energy. But you know that when you release it, it will start to move. So there's some kind of stored energy there. Another example would be if you lift something off off the ground and hold it some height above the ground, if you let go, you'll get some motion out of it. So even though it's not moving when it's up here, there's some kind of stored energy in the system. So those are types of potential energy. And that's super important in chemistry because the type of energy that we're talking about that's in bonds, that's electrons pushing on other electrons or being attracted to protons, there's a stored energy there, right? Because if you release two electrons that are close together and they don't like each other, they're going to fly apart, right? So there's stored energy there. That's electrical potential energy. And that is the energy that drives the chemical reactions. And then third type is thermal energy. It's not really a new type. It's just kind of a way of glomming a whole bunch of things together. And that is inside of an object, right? The temperature is coming from the individual kinetic energies of those individual molecules, right? So instead of talking about the average value, which would be temperature, we could say, what's the total amount of energy in there, right? So the more molecules you have moving, the more energy you would have inside of an object. The larger the object is and the hotter it is, the more energy it has stored inside of it. And of course, it would also depend on what the actual atoms were made out of and stuff like that. And that's called internal energy or thermal energy, right? So it's the amount of like sort of energy that's inside of there due to the actual, mini particles, the little molecules inside of there, instead of thinking about the whole big thing, So like if you raise the thermal energy of an ice cube, right, it will melt. Right. So that's the energy transformation that's going on there, is that the heat and energy that you're pumping into the ice cube, where is it going? It doesn't actually go into making the ice cube move across the room or raise it above the floor, but it is going into its thermal energy or its internal energy. The reason why it's so important to talk about energy is actually what drives everything. Right. So conservation of energy is a universal principle in science. And it really is this accounting of energy, right? If you lose some kinetic energy, you're going to gain it either in potential or thermal, right? And if you lose it in thermal, you're going to gain it in either kinetic or potential, but the total has to be the same afterwards. Even if you let's say I go outside and I get cold, which means my body temperature has gone down, and then I myself am not actually moving, so I don't have any kinetic energy or anything, that energy has to be somewhere. It went out into the environment, like my body heated the air right around me, and now those molecules have the energy, right? So if you look carefully enough, you can find all the energy is still there afterwards. So it can be transformed from those different types. You can transfer it from one object to another, but the total is still the same. That's what conservation of energy means. So let's define heat a little more precisely. This is a word that people use very kind of cavalierly. It is a type of energy, but heat really means specifically the energy that is being transferred from an object that is hotter, that has a higher temperature, to an object that is colder, that has a lower temperature. And it is the energy that is going from the hot to the cold, right? It's not the energy that's stored in the hot object. That's that guy's internal energy or thermal energy. And it's not the energy stored inside of the cold one, because remember, cold objects still have molecules in motion. They're just moving slower. But rather, it's the energy that is going from hot to cold, right? And this is how you determine where to, like a hot and cold object, where the temperature will meet, right? Is because the hot guy will continue transferring energy to the cold guy until they meet in the middle. And I'll show you the formula for that in the middle in a minute. It's not as simple as, of course, they don't always meet halfway, right? Because it depends on their sizes and all those other kind of what they're made out of. And I'll show you that's the formula on the last slide. So two quick definitions here, right? If you're an object that is losing energy, right? So you're releasing energy to your environment or to someone else, that is an exothermic process for you. Exo as in exiting, right? On the other hand, if someone is sending you energy and you're absorbing it, right? You're absorbing the heat, then that is endothermic, right? So exothermic chemical reactions are chemical reactions that release heat, and endothermic ones are ones that absorb it. All right, so here's some questions. I'll read the question, and then the right thing for you to do would be to pause the video and think about what your answer is, and then play and see if we agree. All right, so here's the first one. Which has more thermal energy, an ice cube at 0 degrees Celsius or an iceberg at the same temperature? Okay, so if they're both at 0 degrees Celsius, right, they have the same temperature, which means that their motion is roughly similar, right? The average kind of speed that they're moving around in both the ice cube and the iceberg is the same. That's what it means to have the same temperature. But The iceberg has a lot more molecules in it, right? That's more massive. And so that means you have many more, even though each one of the individual molecules kind of has the same energy on average as each molecule in the ice cube, you have a lot more of them. So the total internal energy or thermal energy of the iceberg is going to be far greater than the ice cube, simply because it has a lot more atoms. Now, if you compare the motion, right, this is the second question, the motion of their internal molecules, like if you look at one from the iceberg and one from the ice cube, you take the average from each more precisely, they will be looking about the same, right? Okay, next question. Which has more thermal energy, a room full of air at 20 degrees or a lead brick at 20 degrees? Okay, so once again, they have the same temperature. So the molecules on average are moving in a similar fashion, right? But you have to think about how many more molecules you have in each situation, right? So you've got the lead brick, which is a solid and a dense solid. So it has many, many atoms in there, whereas the air is made out of gases, which is mostly empty space, right? And so the mass is less. So you're going to go with, when you have two things of equal temperature, you go with the one that has more mass, technically because it has more molecules, right? And so that is why it will have more thermal energy stored inside of it. If a hot teacup is placed on top of an iceberg, which does? Somebody didn't do this very well. Which way, I think, is what I meant to say. Which way does heat flow? Sorry about that. If a hot teacup is placed on top of an iceberg, which way does heat flow? All right. So the iceberg is much larger. So even though it's colder, because it's so much larger, it is going to have more thermal energy in it, right? You could give $1 to 10,000 people, and there's more money there than if you give 10 people, $10, right? You know what I mean? So but it's the temperature difference that dictates which way the energy flows. So since the teacup has a higher temperature, those molecules are all moving around much more quickly. And when they hit the colder molecules, that is the more slowly moving molecules in the iceberg, they will give them more energy, right? Because if a fast thing hits a slow thing, the slow thing tends to, on average, over many collisions, speed up. And the fast thing, on average, tends to slow down. And that's actually how the energy is being transferred, right? The molecules in the hot substance, the hot tea in this case, every collision, they tend to lose some energy and slow down, which means it cools down. And the molecule they hit in the iceberg is speeding up on average. And so the temperature is going up. Now, of course, the iceberg, you're not going to notice much of a temperature difference because that energy is going to quickly get dispersed throughout the many, many particles in the iceberg. So when you put that hot teacup on the iceberg, and if you measure the two temperatures, you'll see the temperature of the tea go almost all the way down to the temperature of the iceberg, and you will barely notice the iceberg temperature going up at all, right? And that's just because the energy being transferred will be equal, but the energy for the iceberg has to heat up the whole iceberg, and so it doesn't really do much work, right? It doesn't do much of a temperature change. Whereas the tiny little teacup, you take that energy away from it, it has a dramatic effect on its temperature. Once again, that relates to the formula that I want to show you in a second. All right, let's talk about the units of heat, which is a type of energy. So kinetic energy, heat, potential energy, thermal energy, they're all measured in these units, right? So the metric unit is joules, Joule. It's named after a French guy, I think from the 1800s, who did a lot of early experiments with energy. And that is defined in the metric system as if you take a 1 Newton object and move it 1 meter, right? And measure how much energy it takes to do that job. And that's what a joule is. Okay, so that's kind of cleanly defined in the metric system. The unit that is, was invented back when they invented the Fahrenheit scale is the calorie. Now, the calorie was adopted by the food industry, and so it's like very hard to go away. I mean, the calorie is a very convenient definition, as you'll see in a second. And so the calorie is more likely, I would predict that it will outlast the Fahrenheit scale. Like people will still be talking about calories, even though the metric system has gone over to joules for many, many years, because it's a super convenient unit if what you're mostly doing is heating down and cooling down things that are mostly made out of water, which of course your food is and your body is, right? And so it's defined this way. It's the amount of energy it takes to take 1 gram of water and raise it 1 degree Celsius, right? So however much energy you have to put in there to do that, that's a calorie. So to translate between the two, you have this conversion factor. 1 calorie is 4.1868 joules. And that would be a conversion factor I give you if you need it, right? Now, there's a trick with the calorie thing, which is when the food industry adopted the calorie. I don't know why they did this. I think it was just because they don't want to put big digits on, when they say this package of Oreos contains like 2,500 calories or whatever. They're actually kilocalories. And they dropped the kilo, right? So they either put a capital C on there or they call it a food calorie. But really they should put a K in there indicating that's a kilocalorie because there's 1,000 of these calories, right? So when you're buying food and you see how many calories it is not the energy that it takes to do 1 gram of water, 1 degree Celsius, right? It's 1 kilogram, right? It's a factor of 3 zeros. So you got to be a little careful with that. All right, so calorimetry, right, is taking that word calorie, and that is the science of actually measuring the heat transfer between things, right? So you put something in an insulated container, and then you measure the temperature, and then you have a chemical reaction, you measure the temperature afterwards, or you put some object in there, and then you burn it, and you see how much it heats up the water, and then you can figure out how much energy was stored in the object, right? That's how the food industry determines food calories, by the way. They burn the food, and they see how much it heats up water from the heat generated from it, and they say, okay, that's the energy in there, right? And they figure that out in calories. So here's the relationship I was promising you about temperature changes. That's the delta T. So the little triangle is the Greek letter delta in this case. And in math, they use that very frequently. If you haven't seen it before, you will see it quite a bit. It means change in, right? So it's a shorthand way of saying it's not T, the temperature. Like if it's 20 degrees, you don't put 20 in there. It's how much did it go up by or how much did it go down by, right? So if you go from 20 to 25, the delta T is 5. If you go from 20 down to 12, the delta T is -8. Right? So it's the change. It's technically the final temperature minus the initial temperature. That's what the delta T is. The M here stands for mass, and the Q is the symbol for heat. Right? So the Q can be measured either in calories, which is probably what people do if they use water, or it should be joules for the metric system. Right? And the mass likewise should be grams, but sometimes they use kilograms. Now, what's the S? The S here is dependent on the material that you're actually heating up or cooling down, right? It's going to be very different if you take 10 grams of water and 10 grams of aluminum foil and you give them the same amount of heat, the temperature is not going to go up the same, right? Because they're made out of different material. They have different molecules in there. And so that S refers to the specific heat capacity, and every different material has its own specific heat. Right. And so what does that mean? If something has a really large specific heat, then that means if S is really big, then that means even small temperature changes will require quite a bit of heat. Right. On the other hand, if something has a really small heat capacity, right, like metals tend to have small heat capacities, then you can get relatively large temperature changes with just small Q values, right? If you just think about it mathematically. And this is why, like, if you take metals and you put them outside in the sunshine, or like all your pans are metal and you put them on a stove, they heat up really fast, right? They heat up in the sunlight, they heat up, and that's because they have low specific heats. They are going to have quick changes in temperatures in response to the heat that you're putting in them. Likewise, they cool down very quickly also. That's why you park your car on a cold day, the car gets cold very quickly. This is the opposite story for water. Water has an incredibly high specific heat, which is good for us because we're mostly made out of water. So we actually hold on to our heat really well, right? So the water value, the 1 calorie value that's defined in terms of water is actually quite a bit of energy, right? If you put a cup of water outside and a piece of metal outside that's the same mass and go back and measure the temperature an hour later after you put them outside, right? The metal will have gone all the way to whatever the temperature is outdoors. And the water will not be, if you've ever tried to boil water or you put try to make ice cubes and put them in the fridge, it takes a while, right? It takes a long time to transfer that amount of energy. So that calorie is a pretty big number actually. And that's the only specific heat value that I would expect you to know because it's the definition of a calorie, right? The specific heat for liquid water is 1 calorie per gram per degree Celsius, right? That's just a different way of saying what I said on the previous slide. If you need to know the specific heat to solve a problem for any other material other than liquid water, I of course will give it to you on the test, or you'd be allowed to look it up. Sometimes, of course, we could give you a problem where we give you all the other variables and then ask you to find the specific heat. That's, of course, how scientists determine the specific heat of these different materials. All right, so it's a new equation. So let's just do a quick example problem. Let's do exactly that. Let's see, how can we determine the specific heat of aluminum, right? So first we would measure out a specific quantity. So I'm going to say 100 grams. And then we will put it in a situation where we know exactly how much energy we're giving it, right? So I'm going to say 900 joules in this case. I just kind of made up these numbers, although I made it work with the actual specific heat of aluminum, right? And then we're going to say it goes from 12 degrees to 22 degrees as we add in that 900 joules, right? So this is how you would use the equation, right? You take your given, so the 900 joules, that's the Q value, that's the heat flow. The mass, of course, is 100 grams. And then we got to figure out the delta T. If you go from 12 up to 22, it's final minus initial. So 22 minus 12 gives you 10. So that's our delta T. So we're going to plug in 10 for delta T, 100 for M, Q for 900, solve it for S, right? And you should keep all the units in there, right? And the units work out to be 0.9 joules per gram per degree Celsius. So the units for specific heat are kind of cumbersome, right? But that is what they are, and you need to respect the units. Hopefully at this point in the course, you understand how important the units are. Okay, that's my introduction to heat and temperature and a little bit of energy.